Hello, scholars. All right, we're on to lesson 3 for Unit 5. We're in the energy unit. Today we're talking about potential energy. The first lesson was about energy in general. Second was about kinetic energy, energy of motion. Today it's potential energy, the energy of position. So, as we talked about last time, scientists like to quantify ideas. They like to put a value, a number on it. So how do we calculate potential energy? Well, we're going to use gravitational potential energy as an example. Okay, gravitational potential energy depends on the object's mass, the acceleration due to gravity, and the height or the relative position of that object. Okay, it's a fairly straightforward equation. Gravitational potential energy equals mass times the acceleration due to gravity. We call that G times height. So gravitational potential energy is equal to mgh, mass times acceleration due to gravity times height. It means the object must have a mass. Object doesn't weigh anything, doesn't have mass, no potential energy. You need to be able to hit something and do work. Remember, energy is that ability to do work. So I need to be able to exert a force over a distance. I need a mass to have a force. Okay? I need to be under some sort of force. We're in the Earth's gravitational field. The Earth is pulling down on us. That gives us the potential to move if we fall, if we move in the Earth's gravitational field. Object also has to have distance. If I'm on the ground and I can't fall any further, well, I don't have any more potential to do work. My position does not give me any future possibility of doing work. Now, if I go to a higher position and I can fall again, now I have a distance to move. All right, let's see how this equation works. Take a look down here. We've got a 1 kilogram mass. Acceleration due to gravity on Earth is 10 meters per second squared. The height is 20 meters. I multiply 1 times 10, I get 10. 10 times 20 is 200. Okay? So I get 200 joules. Notice my units for potential energy are in joules. Same as kinetic energy, same as energy in general, same as work. All the same unit. These are all variations of the same concept. Cool? All right. You know I like to ask about relationships among variables. So what happens when I increase my mass? If I double an object's mass and leave the acceleration height the same, so I go from 1 kilogram to 2 kilograms, what happens to my gravitational potential energy? Acceleration stays the same, height stays the same, my gravitational potential energy doubles, goes from 200 to 400. I double my mass, I double my gravitational potential energy. They are directly proportional. One goes up, other goes up by the same amount, directly proportional. If I double my height, okay, so we go from 20 meters to 40 meters. I keep my mass the same, I keep my acceleration due to gravity the same. When I double my height, 20 to 40, I double my gravitational potential energy from 200 to 400. Therefore, double my height, double my gravitational potential energy, directly proportional. If I double my acceleration due to gravity, so keep my mass the same, 1 to 1. I double my acceleration due to gravity, 10 to 20. Say we go to Jupiter or Saturn or some other planet with a higher gravitational field. Keep my height the same. I double my gravitational potential energy from 200 to 400. So all three of these variables are directly proportional with kinetic energy. One goes up, the other goes up. Kinetic energy goes down when any of them go down. They go up and down by the same factor. They are directly proportional. Now, are there other types of potential energy? Yes. We'll learn about those later, okay? Maybe in high school, okay? Talk a little bit about springs, that's easy, but the other concepts are a little bit harder, not as common to us. Know that they're out there, but we're going to stick with gravitational potential energy. Do your reading. It's only like 2 pages, 448 to 450. Finish your worksheet. I'll see you in class.